So if P is mV, then V is equal to P over M, right? So it's 6.626 E minus 25 divided by 9.11 E minus 31. All right, this is kilogram meters per second divided by kilograms. So divide that by 9.11 E minus 31. And you get a lot of velocity, right? The velocity is and now we're set. The accelerating voltage is going to be 1/2 mv squared over E, right? So basically turn this into joules, divide by that, and you'll get volts, which would be the energy in electron volts, by the way. So I'm going to square this number, which is a velocity. And I'm going to go times 0.5 times 9.11 E minus 31. And I get that it's 2.40965 E minus 19 joules divided by 1.602. And this is coulombs, right? So divided by and I get that it's the voltage is 1.504 joules per coulomb, which is volts, right? Yeah. Does that work? Is that what I got? Hey, that's what I got before. Did I get the answer right on the other one? Yeah, I did. Okay, that's good. Then there's a de Broglie wavelength. The little numbers up there where it says 3, that's the hint. So you can hit the right arrow, 1, 2, 3. That's what they need to know. So they're going to go, oh, what's the mass of the electron? Well, there it is. You know. Lord knows you couldn't look it up in a data packet, right? Okay. And then there it is. But let people get it. Make sure people are doing it. Doing the whiteboards. Punish them if they don't. Momentum of a 600 nanometer photon. Hopefully you don't need to give them the de Broglie equation as a clue, but if you do, beat them over the head too. Right? Electrons in a microscope, so these are pretty basic ones. The first one, I guess, is not quite as basic because you have to use MV as well. Right? This second one's very basic. Electrons are accelerated through 12.8 volts. What is the de Broglie wavelength? Well, this is like the opposite of what we did here. On this whiteboard, you actually have to find the velocity with this, and then you go backwards and go like that, right? And on that one, you can give those formulas as a clue, that first line there. You want to use an electron to have the same wave as the waves on a violin string. I'm just coming up with a creative thing. I thought that was a very creative question. Okay, so one might wonder why an electron might have a wavelength the size of a violin string, but you know, I just couldn't come up with a non-violins way of doing it. There we go. So this is the same as the example, I believe, problem that we did with a different wavelength. Total thrust of the laser. I don't know if you'll get to this one. There are two clues. The total thrust for one photon, that is it. For 5 photons, it's that. And basically, all you have to do is figure out the number. You basically want 1 Newton. Oh, I see. You want to figure out the total total momentum in 1 second is going to be the force. So since that's the number of photons per second, figure out the momentum of one of the photons, multiply by that big number, 9.36 times 10 to the 26 photons, and that will give you the force, which I've worked this out so that it's 1 Newton. And then, of course, you might bring up The movie Star Wars, they had the laser cannons firing away when they obviously were kicking, just like World War II anti-aircraft batteries. And if they were lasers, why, wow, that's, you know, more than 300 megawatts. That would, yeah, put a dent in you, I think. And then you can go on. This next one is just an image. This is an application of it. Obviously, is that you can make matter waves. So this is how electron microscopes work. And the limitation of light is that you can only make an image as small as a light wave. And light waves are as small as 400 or so nanometers, and then smaller than that we can't see them, so they're not visible light anymore. There are a lot of things like DNA, etc., that are smaller than 400 nanometers, and so electron microscopes allow you to resolve things smaller than that by making the wavelength smaller. This is, I believe, a transmission electron microscope. So there's the object right there, and these are very picky. You've got to slice it very thin, and then it goes through. Magnets are used actually as, or electric fields can be used as lenses, because obviously electrons won't go through glass, but they will go through a magnetic field. And that electric field mapping lab we did, is before there were computers that did it, was how you actually made lenses, which is kind of an interesting thing, right? And then Gertrude Rumfer, the sideline there is that, golly, back in the late 90s, I was working at PSU doing research, and she was 80 years old at the time, and she was a world expert at, people would fly her around all over the world to figure out how these, how the lenses, she designed lenses for these electron microscopes. And she had, you know, hundreds of thousands of dollars worth of electron microscopes in the bottom of the Science 2 building. And she showed them to me. I was like, wow. Look kind of like this. They have to have a vacuum in them. That's why it's all stainless steel and stuff like this. And these bolts and everything on there to seal it up. It's got to be a super, super, super good vacuum. This is a scanning one. These are the ones that make the pictures that you see usually. And the idea is that the electron waves are bouncing off the exterior of the surface. So when you later see pictures from electron microscopes, yeah, I think they're all scanning ones. This is a scanner right here. They've got one at OMSI too, which is kind of cool. This is an image from a scanning electron microscope. These are false colors. I think they derive them from the energy of the stuff coming off. And I like to tell kids that this is actually the parasites that live at the base of your eyelashes. It's probably an ant, but I have no idea what it is, but it's cool. Oh no, tell them that this one is the parasite that lives at the base of your, this is a diatom, I think. There's a diatom skeleton. This one's a criminal. That guy lives next door to me. This guy's eating graham crackers. That's a booger. No, human hair, I don't know. Some kind of hair, obviously. It's either human or not, right? And then scanning, tunneling electron microscopes are funny because they, basically it's a probe. They actually just feel for the surface here, and they can measure this distance. They don't touch it, but they get very close to it, and they can sense that. And so basically they make a map of the surface by like this. And they use these for quality control at factories that make chips. Like, golly, I can't remember. What's the one? There's one in Tualatin, and they've got these things, and they float on air, and they're like the size of a Buick, because the slightest vibration really messes these guys up. These are the ones that have imaged, Novellus, that's the company, hit the right arrow. Novellus has these, and they put copper onto chips to make wires, and they can sense the depth down to, you know, atomic diameters, right? And I actually toured Novellus in Tualatin and saw they had a scanning tunneling, scanning tunneling electron microscope. They wouldn't let me go in the room with it though. Like, I so wanted to. And then so finally,